This talk is co-authored with my colleague Diego Murillo Gomez, who's sitting here. So thank you very much for his crucial contribution. So just a few words about the motivation. For our team probably has a main expertise in audio reproduction, really. So we have seen a lot of interesting models to create really realistic, or if you like, accurate, or depending what sense accurate, but models of rooms. So our objective here is to take this information and turn them into kind of the feed for audio reproduction system. Could be either a multi-channel loudspeaker array, set of headphones, or whatever. So the key things is to create a realistic oralization, and probably there are two key ingredients that we want to tackle here. First of all, the spatial audio reproduction. So a single mono impulse response is probably no longer enough to create a convincing oralization. We need to render also the spatial information of the room. So we need, as a matter of fact, a spatial impulse response. That's one thing. The other thing is interactivity, and here by interactivity I mean the ability for the listener to move in the space. And there are a number of techniques that we've tried in that sense, including interpolation of impulse response, or also of ambisonic impulse response, so forth. But we are more concerned about the low frequency ability, so the low frequency feature when you can move around the room and feel the kind of nodes, antinodes in a modal behavior. So with this motivation, what I'm going to do, I'm going to talk a little bit about two main one main aspect of this problem, which is the representation of sound fields for oralization. And specifically, I'm going to talk about two techniques. First one is the plane wave representation. We've heard about that already. And also the spherical harmonics and Bessel function representation. So this is meant to be a little bit of a tutorial, and hopefully could serve a little bit of an introduction for the talk that then John and Angela are going to give. So probably some of you, perhaps all of you, are going to be already familiar with that. I apologize if that is the case. Could be perhaps fresh. We're going to look at how these two techniques are more or less similar in some contexts, but when you reduce the amounts of information, then we will see that they actually are quite different. And then the important thing when we go through that is because this kind of sound field representation allows us to manipulate the sound field. I want to talk about rotation, but there's not going to be enough time. I'm going to focus on translation, so sound field translation, performing sound field translation in the plane wave domain, in the spherical harmonics domain. Might contain equations, so I appreciate that they might be a bit heavier to follow, but I think they are very important. Try to keep it quite simple. So let's start from plane waves. So on the right hand side you can see my kind of reference system, very standard reference system here. And this is standard field for a single frequency of a plane waves. I'm sure you're all familiar with that. I'm going to work mainly for just a single frequency case, right? Work in the frequency domain unless I specify otherwise. So a sound field for a single plane wave called P, the sound field for at a given point in space X. X is the point general position in my sound field. At a given frequency omega. For a single plane wave, it can be expressed mathematically with this expression. We have this standard exponential I, K is the wave number, omega over C. And then we have a scalar product between the position vector x, where we are evaluating our sound field, and this y hat vector, which is the unit vector indicating the direction of arrival of a plane wave. And then we have this factor here as A of y, which represents the complex amplitude, namely amplitude and phase, for the plane waves coming from this direction y hats. In order to simplify the notation, I'm gonna, in the remainder of this talk, I'm gonna use this simplified notation. Instead of using the exponential, I'm gonna use the psi. So psi of x, the evaluation point, y hat is the direction of arrival of the plane wave, omega is the frequency, a is the amplitude. Okay? Now, this is for a single plane wave. We could say that we can represent almost any sound field by superposing a, if you like, infinite number of plane waves. So I could say I have plane waves coming from this direction, and so on. Each of these plane waves with for a single frequency with their own amplitude and phase. So if I superimpose an infinite number of plane waves for all possible directions of arrivals, so if my y hat, you remember the direction of arrival of my plane wave, spans an entire sphere, so I consider all possible direction of plane waves distributed over a sphere, and then they sum all up, well, actually I perform an integral. So this integral here is actually a plane wave superposition, is a superposition of an infinite number of plane waves coming from all possible directions y hat, each of these having their complex amplitude. As you can see, I've dropped the dependency on frequency. So this is one of the key elements for my talk. This is a plane wave, so it's a continuous plane wave distribution, which mathematicians sometimes like to call Herglotz wave function. Just out of curiosity, how many people have heard that already? Herglotz wave function. All right, okay, that's good. So this is a Herglotz wave function. I don't know how rigorous it is in this sense to call it this way, but it sounds very exotic, so let's see. So p of x, again, is an integral for plane waves coming from all directions, each of these with their complex amplitude. Now, this function a of y is now a function, typically lives in an L2 space, and this is sometimes called the Herglotz density, or if you like, amplitude, plane wave amplitude distribution, is a function that, as a matter of fact, contains all the information about the sound field that we want to represent, at least locally. Can we represent really every sound field with this? So is this range, or the range of this operator, really complete for what we need to do? If I were a mathematician, I would tell you no, because if we were to represent a point source, then we have problems, because this function here no longer is living in an L2 space, but I'm an engineer and say, yes, you can do, as long as you're not too fussy about near-field effects. Now, let's look at the other representation, spherical harmonic series. So again, here we have the same sound field P, and this can be represented as a weighted sum of, so we call basis function, they're not rigorous basis function, but mainly we have here on the right-hand side, we have the product of two functions. One is a spherical harmonics. So now I have my point in space x is expressed as the product of x is the modulus of the vector, and x hat is the unit vector identifying the direction in that case. So again, we have here two functions. One is a spherical harmonics that depends only on the angular coordinate, so on the direction of our evaluation point. And then I have here a Bessel function, which depends on the, if you like, radial coordinate and on the wave number. So these two functions are the same for any kind of sound field, represent our basis function, if you like. These here are the spherical harmonic coefficients. Sometimes I think French people call it the Fourier-Bessel series. Is that right? Yeah. Some people do, at least in the French literature on ambisonics, it's called this way. And as I was saying, these coefficients here, b of n, m of omega, are actually a set of coefficients, and they contain all the information about the sound field that we want to represent. Interestingly, in the ambisonics world, these b of n, m of omega are in fact the Fourier transform of the B format signals. So these are the same thing, as a matter of fact. So we have two different kind of representation, and all the information here is contained in this b of n, in this set of coefficients for the spherical harmonic series, whereas for the plane wave case, we have this density function that contains all the information. Going back to the spherical harmonic series, without going into detail how what the spherical harmonics are and what Bessel functions are, just to give you a visual impression of how this we call basis function look like. As a matter of fact, what you see here is a cross-section, horizontal cross-section of a three-dimensional sound field generated with just one spherical harmonic and the corresponding Bessel function. So this is the zero order. Zero, the spherical harmonics, is a zero order Bessel function, and this is the sound field. First order, you can hear this kind of dipole behavior. Second order, third order. So these waves are actually spherical standing waves for a single frequency. So they pulsate, they don't propagate. For those of you who are experienced with Bessel function, you will know that they are the linear superposition of an outgoing spherical wave and an incoming spherical wave. Our result is that we have a standing wave. So we can say that we kind of, if you like, represent our sound field by a linear superposition of spherical standing waves, more or less in the same way as we do in a room when we represent a sound field as a linear superposition of modes, in that case sines and cosines. Interestingly here, you see that when we increase the order, we create a little bit a larger and larger null here at the center. You see, here we have sound field here, but at the center here we have a node, if you like, a larger nodal region and an even larger nodal region. These are very peculiar features of the Bessel function that will be responsible for some difference in representation that we'll see later on. Now, looking at the relation between these two representations, I'm going to introduce this mathematical tool, which is called the Jacobi-Unger expansion, and it serves to express a plane wave. You remember our psi of x of y, so a plane wave psi coming from a direction y hat, in terms of spherical harmonics. So if you like, this mathematical formula is the link between the plane wave world and the spherical harmonic world. And in fact, if we plug this expression, so just an additional word, as you can see, this expression depends only on our field coordinate, x and x hat, and also on the direction of arrival of the plane wave y hat, and obviously on the wave number k. Now, without looking too much in the detail of this expression, if we compare our two representations, so the Herglotz wave function, we remember the integral of plane waves from all possible directions and the corresponding density, my spherical harmonic series with my coefficient b of nm. Now, if I plug this formula into here, and with some mathematical manipulations, or applying orthogonality properties, in fact, and not even here, not even in the orthogonality property, you end up with this result here, which is crucial. So what this is telling us is that the spherical harmonic coefficient b of nm, if you remember, these are the B-format signals, if we're transforming B-format signals, are nothing but the spatial Fourier transform of my plane wave density. This is the key result, right? So the two representations, as long as we use an infinite amount of information, are equivalent. Whether they're exactly the same, we have to see, because we have to see how well behaved this function and this set of coefficients are. But for all practical purposes, they are really identical in a sense. Again, you can regard the B-format signal as the spherical harmonic transform, which is, if you like, a specific case of a generalized Fourier series of our density function, right? Spherical harmonics play more or less the roles of sine and cosines on a sphere, so that the role that the sines and cosines play on a circle, corresponds to kind of the spherical harmonics on a sphere. So the basis function to represent almost any function on a sphere. And you can express almost any function defined on a sphere, as the case of our A, if you remember our plane wave density distribution, in terms of its Fourier coefficient, which are the B-format signals. So I hope you can appreciate this strong link between the two representations. So I could stop my talk here and say, well, that's it, but I won't. And in both in the case of the integral and in the case of spherical harmonic series, we use an infinite amount of information. We need an infinite number of plane waves and an infinite number of spherical basis functions. But in order, you see here, the series here goes to infinity. But what happens if we, for practical purpose, truncate our series to a finite number of spherical harmonics? And we need that, again, we need to approximate the sound field in this way. Now let's see what happens when we try to represent a plane wave by adding increasingly a number of spherical harmonics. So just using the zero order spherical harmonic, we get obviously zero order sound field. We have an exact reconstruction of the plane wave, but only at the center. Then we start adding the first order spherical harmonic and Bessel function, second order, and we see we get a larger sweet spot, if you like the audio terminology. And now going to third and fourth order, you see how the sound field, the reconstructed sound field on the left-hand side looks like. 10th order, we have a very good, very accurate reproduction over an extended area. So you can see by adding an increasing number of spherical harmonic of terms in my series, the area, the region of accurate reconstruction grows, increases, right? And this is again due to this behavior of the Bessel function that we have seen earlier on. You see the 10th order, here the Bessel function of the 10th order, this is for radius 0, almost no contribution at the center. So it's like this kind of spherical wave function, kind of localized spatially, more or less. Now let's look at the plane wave distribution. That's very interesting because the two talks that were given yesterday by Manuel and John at the very beginning, they used a very similar concept. They take this integral here, which is an infinite, if you like, distribution of plane waves from all possible kind of directions, and they're discretized using ideally uniform distributions of directions. So we turn our infinite integral into a finite sum of plane waves coming from a predefined set of directions, and this predefined set of direction, if you like, is a kind of sampling of a sphere, and we try to make it as uniform as possible, which is mathematically hard to define what we mean by uniform, but I think this gives more or less the concept. So instead of having an infinite distribution of direction, we only choose a number of directions, L, for instance, L directions, so we turn this integral into this series. we have our sound field is due to a finite superposition of plane waves. Now let's take a look how now we have reduced the amounts of information, right? We have reduced the number of spherical harmonics, we have reduced the number of plane waves from infinity to a finite number. And let's do a comparison between the two representations. Remember I said when the amount of information is infinite, the two representations are identical. But when we reduce the amounts of information in this way, we sample the Herglotz density and we truncate the spherical harmonic series, this is what we get. So this is a target sound field of a plane wave. This is its representation in terms of a sampled plane wave distribution. And this is its representation, pardon me, in terms of a truncated series of spherical harmonics. Now you see that in this spherical region, now obviously cross-section is a circular region whose ray is n over k, n is the truncation order, or equivalently, to make the comparison fair, is the square root of L, the number of plane waves, minus 1 divided by k. This is because the number of spherical harmonics and the number of plane waves must be the same in order to use the same amount of information. So in this circle here, in both cases the reconstruction is very accurate. But when we move outside of these sweet spots again, if you like, we start seeing distortion. And these are not very obvious here in the case of the sample plane wave distribution, but you can probably see here that there is some distortion. And they are very, very easy to detect in the case of spherical harmonic decomposition. In fact, if we look at the amplitude error, so if you ignore the phase error, just we look at the amplitude, we see that in case of sample plane wave distribution, the overall amplitude, so when it's green, the amplitude is exactly the same. Red, the reconstructed sound field is louder. Blue is quieter. We see that we have a fairly low amplitude error in the case of the sampled plane wave distribution, whereas in the case of the spherical harmonics, because of that feature of the Bessel function, we have that outside of this circle, the reconstructed sound field has an amplitude which is much lower than the original. And this is because we are not including the higher order in our expansion. Again, feature of the Bessel function. One could argue that, well, you are reconstructing a plane wave with a superposition of plane waves. Well, that's obviously is going to be better. Fair enough. Let's try with a different kind of sound field. And this sound field is a fairly peculiar model distribution in a room. So again, we can see that if you reconstruct that in terms of the sample plane wave or the truncated spherical harmonics, you have a very good reconstruction in the circle, which is a very well-known rule of thumb, as they call it sometime. Outside of that region, we see that there is an error for both reconstruction method, both representation, but this error is different. And in fact, if we look at the amplitude error, we see very low amplitude error in this region here, and here we have an alternation of higher amplitude and lower amplitude for the plane wave distribution. For a spherical harmonic case, we mainly have, again, the same results as before. Outside of our circle here, or sphere here, the level of the sound field is lower than the desired one. Why is this all important? Well, we can look at the translation now. What do I mean by translation? It's important for oralization because when you move from, let's assume this is a plane wave now in the time domain, all right? I have a plane wave in the time domain. This is our listening position. And at our listening position, we can represent our sound field in terms of our A of y. If you remember, this is the function that tells for each possible direction what is the complex amplitude of the plane wave. In this very specific case, it's going to be just a Dirac delta pointing in this direction. So you only have a single plane wave, right? So what happens when the listener translates to a different position, which is what you would have with interactive oralization, right? So when you translate, you have a new density for your Herglotz wave function, which is called A of t, is the translated density. But in the case of the plane wave, this is very simple, because if you translate here, all you have to do is to delay this plane wave by this amount. Does it make sense? You just translate from here to here, and you want to represent the sound field to this plane wave, well, you only have to delay it. In the frequency domain, this is corresponding to multiplication by a complex exponential corresponding to this distance. But this holds for this plane wave. If you have a different plane wave, then you obviously have to delay them differently. The plane waves come from this direction, you have to anticipate that plane wave. So I don't have the time to go through all the math, but if you want to express, if you like, extrapolate your sound field representation, if you have the description of your sound field here in terms of plane wave distribution, and you want to represent it for a different location, all you have to do to obtain this translated Herglotz density, or if you like plane wave amplitude distribution, is to multiply the original amplitude by a complex exponential. In the time domain there would be a delay that depends on y hats. Make sense? So you delay some plane waves, you anticipate some others. If a plane wave is coming from here and you move in this direction, there is no change. Okay? So from a practical implementation, this translation is very simple because all you have to do is to apply delays, so angular dependent delays, to your set of plane waves. Let's do now in the spherical harmonics domain. It's quite complicated. Forget this about for a second. Just look at this one. So, well, let's assume that we move from here to here. So when you translate, we want to compute our translated set of spherical harmonic coefficients, if you like, our translated set of B-format signal from the original one. You can do it in the spherical harmonics domain, but it's extremely complicated. So if this is our sound field, so we have P of x is a linear superposition of our usual spherical harmonic and Bessel functions times the translated B-format signal. Then it's very complex why you obtain this result, but trust me, this is this way. It is this way. Each translated B-format signal is a linear combination of all the other B-format signal. So if you think about it, this is a convolution in the spherical harmonic domain, because each translated coefficients depend on all the other coefficients B of nu mu. So whilst we have in this case a very simple translation, and in fact it's a simple multiplication, if you want to apply a convolution theorem, if the translation is a multiplication in this domain, it's going to be a convolution in this other domain, the Fourier domain. So this is very complicated. But there is also another significant issue. In the time domain, when we represent the sound field in terms of spherical harmonics, a plane wave turns into a circular wave, a spherical wave, which is louder here in the direction of arrival, but we have also what sometimes are called the side lobes. So as a matter of fact, it's a circular wave. Now if we translate here, then we have, because of the precedence effect, this side lobe will arrive first, so that the error we create is significant in this case. So this is just for a single frequency. This is our target sound field. If we are here and we translate inside this circle of exact reconstruction, is all good. But when we move outside of the circle here, and remember the region, the area of this circle here depends on frequency. When we move outside, depending on the representation we are using, plane wave or truncated series, we're going to have different errors in practice. Now, this is just the advertising here, the work that Diego has done. So he has implemented a piece of code that implements the translation and rotation in the plane wave domain. Actually, the rotation is in the spherical harmonics domain, while the translation is in the plane wave domain. And what it should demonstrate is if you are in a room with different kind of modal behavior, you have nodes and antinodes. So if you move around, you can experience the different kind of level at the nodal frequency, depending on where you are in your sound field, all based on this kind of sound field extrapolation, based mainly on delay of plane waves. And it's going to give a demo for those of you who are interested later on. That concludes my talk. So very briefly, I've introduced the two representations, spherical harmonics representation, plane wave representation. I've shown that when we use an infinite amount of information, the two representations are practically equivalent. But when we truncate, so the spherical harmonic series always sample our plane wave distribution, then within the region defined by a sphere of radius n over k, then we have a fairly accurate reproduction or reconstruction of a sound field. Outside that region, the two representations yield different errors, if you like. And then we have seen how we can do the translation in the two domains, the spherical harmonics translation and the plane wave translation. One is simple, the other is more complicated, depending on what you like. But also, when you apply the translation to different domains, the results that you get is different depending on what approach, what representation you use. And that's all. Thank you very much.